Hi, I'm Andrew Nagy with Arrowhive Networks, and today I'd like to talk to you about high-density Wi-Fi design. And one of the first steps in designing a high-density Wi-Fi network is requirements gathering. High-density Wi-Fi networks are becoming much more prevalent today than they were in the past. Most people think of high-density Wi-Fi networks as only being in stadiums, large lecture halls and universities, and things of that nature. But actually, high-density Wi-Fi networks are becoming much more prevalent in common organizations for conference rooms, meeting rooms, cubicle space, and even common areas. And in education within classrooms as well. The reason for this is because Wi-Fi networks in the past were designed around coverage as the major design variable. Did clients have an adequate signal-to-noise ratio and RSSI at a given distance from the AP, and to make sure we had coverage throughout the entire facility? As we have more clients coming into common Wi-Fi networks, we find ourselves being limited by capacity. And so capacity is becoming just as equally important in designing a Wi-Fi network as coverage has been in the past. So anywhere where a single access point can provide coverage but not enough capacity, we need to start thinking about designing Wi-Fi networks differently. We need to start taking into account client capabilities and application throughput capabilities in order to make sure we have enough capacity for the Wi-Fi network. And this is because Wi-Fi uses over-the-air transmissions, or RF. And in this case, airtime is the limited resource that multiple clients are contending for. With limited airtime, each client only gets a piece of the pie, or a piece of that RF spectrum to use at a given time. Therefore, we need to design with all the client capabilities in mind and the mix of those clients in the environment to understand how much airtime each client is going to be using in order to properly design our network for the adequate amount of capacity. So we can highlight this with a simple drawing of an access point. If we have one client connect, let's take a simple example of a laptop. Now, if we take this laptop's capabilities into account, let's say it's a 3x3 MIMO, and is capable of 450 megabits per second. Its actual TCP/IP throughput will be anywhere between 40 to 60% of the raw data rate. And this is because of overhead on the Wi-Fi network. For this example, we'll make it very simple. We'll just use 50% of the actual raw data rate is actual TCP/IP throughput. So in this case, we'll say 225 megabits per second is the actual TCP/IP throughput, whereas this one's the raw. If he's the only device on the access point, this means that he has no contention for the airtime with any other clients, and he can probably get all 225 megabits per second through. And this usually results in about 80 to 90% of channel utilization over the air on that frequency or on that channel. But to highlight how different devices interacting on the same frequency and the same channel impact the capacity of an access point and of the network, let's add in a second device to this example. So let's say we have a second device and it's a tablet device. This tablet is a 1x1 MIMO capable of 65 megabits per second raw. And that translates into, let's say, 30 megabits per second of actual TCP/IP throughput. Now, in an equal scenario where both devices have equal airtime, this will result in both getting approximately, let's say 50%, just to make it simple, airtime on that AP radio. This means that if the laptop previously got 225 megabits per second when it was the only device, now it's only getting maybe 110 megabits per second under this new scenario, sharing the airtime with this tablet. And this tablet, because it's only capable of 30 megabits of actual TCP/IP throughput, if it's using half of the airtime, let's say it gets maybe 15 megabits per second. We add those two together, and we've got 125 megabits per second of actual throughput now when the airtime is shared between those two devices. And it's a split between the two devices reflecting their individual capabilities. So we can see right away that the capacity of this single channel has gone down from 225 megabits to 125 megabits just by introducing the interactions between multiple stations on the same channel. That's a very easy way to see on a very simple scenario or a very simple example how the interactions between devices affect one another on the wireless network. because that's a shared airtime and shared RF medium. So it's important when we're designing high-density Wi-Fi networks that the capacity that we take into account is not just based on what access point we buy. It could be a low-end AP, it could be a high-end AP. It's going to be the interaction between the AP and its capabilities along with all of the client devices on the channel and on the same frequency, and all of their unique individual capabilities, and the interactions between those that govern the actual capacity of the network. So when we're thinking about doing requirements planning for a high-density Wi-Fi network, we need to go through a process to plan out exactly and map out exactly what those client and AP capabilities are. We start by taking a client inventory. So we wanted to understand what client devices and what types of devices are coming into the network, as well as plan for multiple devices per user. Today, users are carrying anywhere between 2 and 3 devices, usually some form of a laptop, a tablet, and a smartphone. 2 of those 3 may be using multiple even at once. We need to understand what's being brought into the environment, and having a tool in your infrastructure that can report on client device type and operating system is very useful. Second, we need to understand the client and the access point's radio capabilities, because the different mixture of these unique variables is what determines their interaction and the ultimate capacity on the wireless network that you can plan for. So we need to understand what the radio capabilities are, such as multiple input, multiple output, and spatial division multiplexing. How many spatial streams can each client support? What channel width can each of those clients support? And what are we designing our network for in terms of channel width on the access points? Are we doing 20 megahertz or 40 megahertz channels? And that will impact how much airtime is required for each client to get through the amount of data for the application that the user is using. We also need to understand channel support in order to understand and to plan our network during the site surveying process, what channels can and can't be used so we don't end up with any coverage holes for certain clients that maybe don't support, let's say, the dynamic frequency selection bands in 5 gigahertz. Third, we need to understand application throughput. So once we have, let's say, the raw specifications for a client device like 3x3 MIMO and a raw data rate of 450 megabits per second with an actual data rate or actual throughput of 225 megabits per second, we need to understand what application is the user going to be using in this environment on that device. Because if a user is using a high bandwidth application, they're going to be using more airtime than if they're using a low bandwidth application. And the same application being used on different device types can take different amounts of airtime or different capacity on the network in order to get that data through. So for instance, both of these devices, a laptop and a tablet, if they were both doing the same application, the tablet would take significantly longer or more airtime in order to get that same data through as the laptop would, because it's a slower speed client. Once we understand the application throughput for every user or every device type, then we can actually start forecasting AP capacity as an initial starting point into our RF design process. To forecast the initial design, or to forecast the initial access point capacity, we need to take the full interaction of all the devices that are anticipated on the network. So to take an example here, we're going to do 2 examples. The first one, we'll take an example of 30 tablet devices in a classroom environment, and the lecture is based on, let's say, a 2 megabits per second streaming video. So here we have an access point in a classroom environment, or perhaps multiple access points, that's what we're determining. We've got 30 tablet devices, so 30 of these guys. They're all going to be doing 2 megabits per second streaming video. That's our application throughput that each requires. So these tablets, we're going to say, are 1x1 MIMO, capable of 65 megabits per second, and an actual TCP/IP throughput then of 30 megabits per second. So to understand how many access points, radios, and channels we need to support all 30 of these tablets in a classroom, we need to understand how much airtime each one is going to use in order to get through that 2 megabits per second video. So here we take 2 megabits per second, divide it by the actual capability of the client device, which is 30 megabits per second of actual TCP/IP throughput, and that gives us approximately 7% airtime that each client device is required in order to get the desired application throughput. If we have 30 devices times 7%, we have 210% required airtime in order to serve all 30 tablet devices concurrently. And what this means is, if each AP radio or each channel is 100%, we would need at least 3 AP radios in order to serve all 30 tablet devices at once. That's going to translate typically into 2 access points that have dual radios, one on 2.4 and one on 5, and we'll have some headroom for growth, or perhaps to support a little bit higher bandwidth application for every tablet device. So that's a very simple example using a homogeneous environment with all tablets. For a second example, let's take one that's a little bit more complex. So for a second example, let's take more of a heterogeneous environment where we have a mixture of client device types. So let's say we're planning a lecture hall in a large university, and we're going to plan for 200 users. These 200 users are going to bring in 2 devices each, maybe a laptop and a tablet. So we're going to have 400 total devices, and this accounts for 200 laptops and 200 tablets. Now the laptops are, let's plan for 2 spatial stream, because maybe we have some lower end laptops. We don't know exactly what the students are going to bring in. We're going to plan a little bit worst case scenario rather than assuming they have the latest and greatest. Maybe they're on a low budget or something. So they have 2 spatial stream capable of 300 megabits per second raw, or 150 megabits per second of actual TCP/IP per client. And the tablets are 1 spatial stream devices. Therefore, they're capable of 65 megabits per second, or 30 megabits per second of actual TCP/IP throughput. Now, for an application, we're going to assume that each client is doing some casual web browsing, email, and taking notes during the lecture. Let's give them just an assumed value of 1 megabits per second. That is the minimum threshold that we want to be able to provide to every client. So our application throughput in this case is 1 megabits per second, whether they're on a laptop or a tablet. Now, for the laptop device, we need to figure out how much airtime each device will take in order to get through that 1 megabits per second of data. So for the laptop, we take 1 megabits per second divided by what each one is capable of, which is 150 megabits per second. And that gives us an airtime utilization for each device of 0.66%. We have 200 of these devices in the environment, so we'll multiply by 200 to account for all the devices in the lecture hall. And that means we need 133% airtime total in order to serve all 200 laptops. So obviously 1 access point radio on 1 channel is not enough. We'll need at least 2 radios or dual radio access point in order to serve all the laptops. For the tablets, they're needing the 1 megabits per second, but they're only capable of 30 megabits per second of actual throughput. So the airtime utilized by every tablet device is going to be higher. It's going to be 3.33%. So already you can see the disparity for the same application throughput, that the tablet requires much more airtime than the laptop. We have 200 tablet devices, so we'll go ahead and multiply that out, and we'll end up with a total airtime utilization for all 200 tablets of 666%. We add the 2 together because we need to support all of these in the same environment, and we end up with 800% airtime utilization. Now, if every access point radio on a single channel can serve 100% airtime, that would equal 8 access point radios. But in the real world, not every access point radio on a single channel can max out the airtime utilization to 100%. We typically see airtime saturate around 80%. So if we divide 800% by 80%, which is the realistic maximum airtime utilization on a channel, we end up with 10. So we need 10 access point radios in this lecture hall to simultaneously serve 200 laptops and 200 tablets. This can be 5 dual radio access points or any combination in between. So if you'd like more information on designing high-density Wi-Fi networks, you can check the Aerohive website, and on this blog we'll link to the Aerohive High Density Wi-Fi Design Principles white paper, as well as the Aerohive High Density Wi-Fi Design and Configuration Guide. Thank you.